In this video, we're going to start looking at the integrals of trigonometric functions. Now, in the Advanced and Extension 1 courses, you should have already come across some trigonometric functions and their integrals. In the Advanced course, you would have come across the integral of sine, the integral of cos, the integral of sec squared and cosec squared. The integrals of tan and cot, now, although they're not explicitly taught in the Advanced course, as in something that you should memorize, or it's not something that's given on a standard integral sheet, the techniques used to solve them are taught in the 2-unit course, or the Advanced course. Okay, so these are definitely included, or I would definitely include those in Advanced. The last two, the integral of sine squared and cos squared, are things that you should come across in the Extension 1 course, and they utilize the use of the double angle formulas. So now let's get into some examples of trig functions that you only see in the Extension 2 course. The first kind of integral that we're going to look at are the integrals of odd powers of cos and sine. So here in our first example, we have the integral of cos cubed x. Now the way that we do these is we want to usually reduce the power of cos or sine by 1. And what we mean by that is we want to just multiply by cos x. So to make up a power of 3, I have to multiply this by cos squared x. The purpose for this is because we know a nice identity that involves an even power of cos and sine, and that's that cos squared plus sine squared is equal to 1. So if we're able to use, or if we're able to pull out a cos squared or a sine squared, then we'll be able to use this identity. So how do we do that? Well, this is going to give us cos x times, we can rearrange that identity to give cos squared equals 1 minus sine squared. And this is actually going to be very beneficial. If we expand this out, we'll get cos x minus cos x sine squared x. And then we can actually split this into two integrals. Now I'm going to write out all the steps for the first example, but once you become confident with it, you don't need to do all these steps. It's going to be two integrals, the integral of cos x minus the integral of cos x sine squared x. Alright, now the first integral is pretty standard. This should just be sine x. The second integral, however, we can think of this as f of x to some power n, and this is f dash of x. And if you've been following along in the playlist, you should know how to do this quite easily. You could make the substitution, let's write the substitution here. You could make the substitution u equals f of x, which in this case is sine x, or you could just make a mental substitution and do it in your head. And if you do that, either way, you'll get sine cubed x over 3, and then plus c. And that would be our final answer. The second example is the integral of sine to the power 5x. Again, we want to do a similar thing here. We want to make this the integral of sine x times sine to the power 4x. So the idea, once again, is to bring out one of the sines or the coses, depending on what function you have, and then have that being multiplied by an even power of sine or cos. And here, what we're going to do is we're going to recognize that sine to the power 4 is actually sine squared or squared. And then that would allow us to use our Pythagorean identity. So this will be sine x times, well, what is sine squared? Sine squared is 1 minus cos squared. And then because sine to the power 4 is sine squared squared, this has to be squared. Now we can expand that bracket there. So we have sine x times 1 minus 2 cos squared x plus cos to the power 4x dx. We distribute the sine x through that bracket, and we get sine x minus 2 sine x cos x or cos squared x, plus sine x times cos to the power 4x. Let's move this up a little. Okay, now once again, what we're going to do, let's get rid of this equal sign. We're going to recognize that a lot of these functions are in the form of f dash x times f of x to the power n. Again, in this one, it's f dash x times f of x to the power n. If you're not comfortable with doing the mental substitution, that's fine. You would make the substitution u equals cos x. Okay, so the first integral is the integral of sine x. That's pretty standard. That's minus cos x. Okay, now we need to be a little bit careful. F of x is cos here in this second part. F of x is cos, and the derivative of cos is negative sine. So we do have a negative sign here. Let's highlight it, and maybe in yellow. Here's our negative, and here's sine. So we'll be left over with 2 times, we raise the power by 1, so cos cubed x divided by 3. Okay, let's see what happens here. Again, f of x is cos. The derivative of cos is negative sine. We don't actually have a negative sign, we have a positive here. So this needs to become a negative, so that we have 2 negatives to make the positive. Cos to the power 5x over 5, and then plus c. And that would be our final answer. So we have a rule by which we can summarize the previous 2 examples. When we're integrating an odd power of sine, the power can be reduced by 1 by factoring out a sine x, and then using the Pythagorean identity on the remaining even power of sine. After that, you can make the substitution u equals sine x, or as I did, you can make the mental substitution. So now we're going to have a look at how to integrate the even powers of cos and sine. And this is something that we've already touched on in the Extension 1 course. We've integrated sine squared and cos squared. And to do that, we utilized the double angle formula for cos. So we looked at cos 2 theta. And remember, there were a few ways that we could write cos 2 theta. And what we did was we rearranged those to have expressions for sine squared and cos squared. So for sine squared, that was a half 1 minus cos 2 theta. And for cos squared, it was very similar. It was a half 1 plus cos 2 theta. Now, when we're dealing with higher even powers, so for example here sine to the power 4x, we want to exploit this fact here. In particular this one, since we're dealing with sine in this case. So sine to the power 4, we want to include sine squared in that. And that's not too difficult to do. Sine to the power 4 is just sine squared all squared. So here we included sine squared, and then we raise it to whatever power is necessary. In this case, it's another power of 2. So now we can make our substitution. For this sine squared here, we can use our formula, the one that includes the double angle. So that's going to be a half 1 minus cos 2 theta all squared. That should include the half, all being squared. And I wrote theta, but that should really be an x because we're dealing with x's. Okay, now this isn't really too difficult to deal with. We can just expand this out a little bit. So the half gets squared, and that becomes a quarter, and I might just take that out the front. And then expanding 1 minus cos 2x squared would give us 1 minus 2 cos 2x plus cos squared of 2x dx. Okay. Let's start integrating this. The integral of 1 is x, put a big bracket around this, minus the integral of 2 cos 2x. Well, the integral of cos 2x is going to be sine 2x on 2, and then we still have that 2 that's sitting out the front. You can see that these are going to cancel. And then we still have this integral, the integral of cos squared 2x. Let's just write it like this for the moment. Take it one step at a time. And remember, all of that bracket is being multiplied by a quarter. So we're going to distribute that quarter through right now. So we'll have x on 4. We already saw that these 2's will cancel, so we'll have minus sine 2x on 4 plus a quarter of this integral. Now, how do we integrate cos squared? Well, that's using this formula right here. So we're going to have the integral of a half 1 plus cos of twice the angle, and the angle here is 2x, so twice the angle will be 4x. Okay, let's move up a little bit, and now we just compute this last integral. So we have sine 2x on 4. If I take that half out, that will give me 1 on 8. Then I have the integral of 1, which is x, and cos of 4x, not to the power, cos of 4x is going to be sine 4x on 4 plus c. And if I really wanted to, I probably should, I have x on 4 plus 1 on 8x. That's going to be, let's see, 3x on 8 minus sine 2x on 4 plus sine 4x on 16, not 16, 32 plus c. And that is our final answer. We also have a rule by which we can summarize how to deal with even powers of sine and cos. So if we're integrating sine to the power 2kx, which is just another way of saying sine to an even power, we rewrite the function as sine squared to the power k. And then we make use of the double angle formulas. Now we substitute in sine squared, the formula for sine squared, and then we need to expand that. After we expand, we're going to have to use more double angle formulas again. Okay, and that's just going to have to keep repeating until finally we have no more squared terms. And then we can do straight integration.